Okay, folks, time for another video lecture. We're going to depart now from talking about motion, which we spent most of the year on, and actually get into some special subjects within physics that don't have anything to do with kinematics or dynamics or anything like that. The first of these units is going to be on electric forces and electric fields. So let's get into it. Hopefully you've all had some exposure to some of this content in some of your other classes. Electric charge, which you've talked about as regards protons and electrons and so on, is a property of a substance that determines how it interacts with other charged particles. So think about, for example, an electron. How do electrons behave when they're around other electrons? And how does that behave, or what is the difference there with how it behaves around protons? When we talk about electric charges, they come in two different forms. Negative charges, of course, in the form of electrons, and positive charges in the form of protons. Think for a minute about where each of those types of charges are kept inside an atom. Whether a substance overall has a positive or negative charge is determined by whether it has more protons or electrons. If it has more electrons than protons, it will have a negative charge. If it has more protons than electrons, instead it will have a positive charge. If something has an equal amount of positive and negative charge, the object will be electrically neutral. Most of the time when you work with, say, atoms while doing chemistry problems, you're going to assume most of the time that they have a neutral charge. Of course, in nature, there are very few things that are just floating around completely electrically neutral. Most things in nature react with other substances, resulting in a transfer of electrons, which of course changes the charge state of the atoms involved in the bonds. Electric charge follows the rule that opposites attract. Things with positive charges are attracted to things with negative charges and vice versa. In addition, two negatively charged objects will move away from each other, just like two positively charged objects will move away from each other. We'll see an example of this phenomenon when we play with the Van de Graaff generator in class tomorrow. The unit for electric charge has a specific value. It is quantized. When we talk about something that's quantized, we mean it always occurs in a set amount that we assign a value for. One quantized unit you may be familiar with is the dozen. If you go to the grocery store and you ask for a dozen donuts, you're expecting to get 12 donuts. For electric charge, the variable that represents the quantized amount of charge is called E. We can have positive values of E, that is multiples of 2E, 3, or what have you, or negative values as well. So how does that work in terms of charge and figuring out the total charge that an object possesses? Well, E has a value of 1.6 times 10 to the negative 19th coulombs. The coulomb is the unit of electric charge. Every charged particle and every substance in the universe, for that matter, has some overall charge that's a multiple of 1.6 times 10 to the negative 19th. It could be positive or it could be negative, but it's still evenly divisible by 1.6 times 10 to the negative 19th coulombs. Notice how we have a balance there between a positive and negative value for E. If we want to know the overall charge of an object, all we have to do is count up the amount of charge of its protons and of its electrons and see which one is greater. If they have the same number of protons and electrons, then we'll end up with an overall charge value mathematically of 0 coulombs. Now let's move on a bit to talking about the nature of electric charge and how it interacts with substances that carry it. If we have a substance that easily transfers electrons, we typically refer to it as a conductor, like the people who run choo-choo trains. Hee hee, choo-choo train. Seriously though, what types of substances typically make good conductors of electricity? Think about that for a moment, then move on to the next part of the presentation when you're ready. In general, the best conductors in nature are going to be solids, in particular metals. Metals have their atoms in close proximity to each other. That means it doesn't take much energy for an electron to jump from one metal atom to another. Something else that I'm just going to add there that's not necessarily mentioned in the previous slide is that metals also tend to have a very loose grip on their electrons. They go through something called electron shielding, where the electrons on the outside of the electron cloud in the metal atom are protected from the attraction they have to the protons in the nucleus by the inner electrons. So think of it like this. You have electrons floating around on the very outside of the atom. Now they're going to have some kind of electrical attraction to the protons in the center. But since there are electrons in the middle of the cloud that help repel those outer electrons, because of course they both have a negative charge, the electrons on the outside are not as attracted to the protons in the nucleus as they might otherwise be. So that's another factor that affects why metals in particular are very good conductors of electricity. On the flip side, however, we have insulators. These are things that are poor conductors of electricity. So think about how we talked about the abundance of charge in metals and the characteristics of metal atoms. For something that is an electrical insulator, what would you expect the arrangement to be for its particles? Think about your answer, then move on when you're ready. For a substance that's an insulator, they typically have large gaps between their atoms, which makes it hard for electrons to jump from atom to atom. This is why gases and liquids are usually pretty poor conductors of electrical energy. You have to put a lot of energy through most gases or liquids in order for it to conduct electricity. Sometimes you can also get good insulators out of objects that, unlike the metals, keep a tight grip on their electrons. Wood, for example, is not a particularly good insulator or a conductor of electricity. It's quite a good insulator. Its atoms don't easily want to give up their electrons. So now that we've talked a little bit about what makes good conductors and insulators, let's talk about how we actually bring about electrical charge in substances. The most common way that you're probably familiar with in terms of actually charging something would be through something called charging by contact. So at some point, I'm willing to bet that you've done the experiment, and I certainly know you have if you've been through one of my classes in the past, where you take a balloon and you rub it against your hair. By doing that, you can make your hair stand on end, and you can make your balloon pick up little pieces of paper or stick to the wall or perform all kinds of other little tricks. When you do this, you are charging the balloon and your hair by contact, through the physical interaction of the particles in the balloon and the particles in your hair. Another way of charging a substance is through charging it by induction. Charging something through induction means you're going to bring a negative charge near that object and then allow the electrons in the neutral object to move away out of the neutral object through a wire or some other escape source, typically referred to as a ground. If you've ever heard about the need to be grounded or something like that while working with electrical equipment, that's where the term comes from. Induction can be seen as shepherding electrons. This means we're going to force them out of an object because the electrons in the neutral object don't want to be around the electrons in a negatively charged object. This is due to the repulsion of substances that have the same electric charge. Other electrons really don't want to be around other electrons. Seen here to the right is a border collie. They're great dogs. They have tons of energy, and they've been known to play a mean violin. So in this diagram you see here, we have a negatively charged balloon that we've brought near a piece of metal that's part of a device called an electroscope. An electroscope consists of essentially two pieces of metal, one that doesn't move, and then a movable piece that's some type of needle, piece of aluminum foil, or something like that. What we're going to do is bring the negatively charged balloon near the electroscope. As we do that, the electrons in the electroscope want to move as far away from that balloon as possible. Now that by itself doesn't charge our object because it still has the same number of protons and electrons than it had before. But if you'll notice at the very end of the particular presentation, the electrons will leave the electroscope if presented with a way to leave. The way for them to leave is through someone's finger after that person touches the electroscope. By touching the electroscope, the person allows electric charge to flow out of the electroscope, leaving it with an overall positive charge. Now let's think about why that happened. If electric charge in the form of electrons leaves the electroscope, there's only going to be, well, there will be more positive charge than there was before. Obviously the atoms inside the electroscope will still have some electrons around them, but just not quite as many as they had before. Typically, this process only works well with conductive substances. Insulators don't work so well at just giving up their electrons because a negatively charged object happens to come near them. A process similar to charging an object, but not actually a type of charging, is called polarization. If you polarize something, you force one part of it to be positive and one part of it to be negatively charged. The object overall, however, still has the same charge that it did previously. So let's look at polarizing through an example again using a negatively charged balloon. We have a soda can that's sitting on an insulating base. We bring the negatively charged balloon near the cola can, and the electrons in the can move away from the balloon. There are negative charges then on the side opposite the balloon, and positive charges on the side closest to the cola can. Polarization explains why objects like a charged balloon can do neat tricks like picking up pieces of paper. The negatively charged balloon forces electrons in the paper to the opposite side away from the balloon. There's now more positive charge than there was before on the side of the balloon closest, or the side of the paper closest to the balloon, which means that there's now an electrical attraction between the balloon and the paper. Again, and I cannot emphasize this enough, the paper itself still has the same charge that it did before. It's just that the positive charge now on the surface of that paper wants to get with the balloon, so it does. The charge that we induce at the surface of an object is called a surface charge. Basically, this is any situation that occurs when electrons are pushed away from the surface of an object by an incoming negatively charged object. Object still has a neutral charge overall because it lost or gained any charged particles. At this point, there's one last thing I want to mention before I end the discussion today. Think for a moment about why all of these different methods of charging that we've talked about and polarization occur when electrons move and not protons. Why is it that electrons are always the charged particle that moves around when charge is distributed or changes in an object, and not the protons inside the nucleus of atoms? What I want you to do as a homework assignment is look up the answer for this question and have it as part of your notes. I'll be checking for that tomorrow. Good night and good luck.